Hey everyone, Katrina here, and today we're going to talk about separable equations. Be sure to subscribe for more videos like this and watch to the end to see the examples. Okay, so this video is my first in the series of first order ordinary differential equations. We're going to be looking at separable equations today, and I'm going to show you a step-by-step method on how to solve them every single time. So the first thing that I want to point out is the structure of separable equations. Separable equations will have the form dy over dx, usually on the left-hand side. So this is the derivative of y with respect to x. And then on the right-hand side here, you'll see that you have the multiplication of two different functions. One function will be in terms of a variable x, for example, and the other function will be with respect to another variable, for example, variable y. So this is a general form of separable equations. Just note that when you're working through problems, it might not always be perfectly in this format right away. You might have to do some algebraic manipulation to uncover if it is truly separable or not. But just beware, because these are one of the easiest and most fun differential equations to solve, so always check if you have a separable one first. Okay, so let's go through the steps over here. So starting with step 1, you want to separate both your x and your y terms, just like I showed above, that you have these two kind of separate functions up here. Once you have that, we're going to move on to step 2, which simply is to integrate both sides of your equation. So ideally, after you've separated them, you're going to do some manipulation such that you have your y terms and one side of the equation, and then you have your x terms on the other side of the equation. And then in order to solve this, all you have to do is integrate both sides. So what I'm going to do now is I'm going to walk you through a generic way how to find the formula, and then we're going to go through an example with real numbers. So be sure to watch for that one as well. So let's start with this kind of generic form over here. So say we have our function over here that is dy over dx, right? And it equals to our equation above, which is, we'll just say r times p. So in this case, like I said, we need to separate both our x and y terms. And like we mentioned, our r is in terms of x and our p is in terms of y. So all we have to do is just kind of do some division and multiplication to move this stuff around. So the first thing I'm going to do is I'm going to multiply my d of x up to this side, meaning that I'm multiplying dx on both sides of the equation, so it cancels out on the left side. That is going to give me dy equals to rx py and then dx, okay? Next, I need to get my y terms all together. So I'm going to divide both sides of the equation by py. So we end up canceling it out on this side, and as a result, we have that 1 over py dy equals to rx dx. And have we done it? Yes, we have. So we've separated our x and y terms such that on our right-hand side of equations, we only have our x terms, and then on our left-hand side of the equation, we only have our y terms. So this means that we are ready now for step 2, which is to integrate, okay? So let's do that. Why don't we add our integration in green over here? So we have integrate both sides of our equation, and let's see what we have next. So this is the typical form of integration. So you can think we have like 1 over y. What is the integral of that? Well, that's just ln of py. Okay, and we always have to put the absolute values whenever we integrate these like rational functions, because ln, which is a natural logarithm, can only take positive numbers in its domain. That's why we must have these absolute value brackets. And then integrating Rx on this side, well, the integration there is simply just going to be x multiplied by our Rx function. And then we have to add our plus c prime. And our c prime here, well, what is this? This is our integration constant. So whenever we have an integral without our bounds of integration defined, so when we have an indefinite integral, we always have to add this arbitrary integration constant to the end of our integral. So again, this is just the generic integration. So basically whenever you integrate it, you add an extra power of x. So this is just our generic one here. Since we're integrating with respect to x, there's our x over there. Okay, so what do we have to do next? Next, we always want to solve for y. So that is the purpose of solving this differential equation, is we need an answer in terms of y. So how can we now rearrange for y in our equation? The first thing we need to do is free the y from the ln. Okay, so what is the inverse operation to ln? Well, that is e. So what we're going to do here actually is we're just going to bring both sides up so that they're now the exponent of our exponential function. Why does this work? Well, this is a special little math kind of magic trick here. We know that e to the ln x, for example, or we just write it like this, e to the ln x equals 2x. So this kind of cancels itself out. So that will allow us to free essentially the y from that side of the equation. So over here, we now have the absolute value of p of y equals to e to the x r of x plus c prime. Okay, so now what can we do? Well, the first thing we can do is looking at our exponential rules. We know that if we have an addition within our exponent, we can actually have this as a multiplication with the same base, meaning that we would have e to the x rx multiplied by e to the c prime. So we can take the same base, which was our e, and just have that exponent over there because we had the addition. Okay, so now what are we going to do about this absolute value sign? So absolute value sign means you can just take the positive and negative. So that means that our py here equals to plus or minus e to the x rx times e to the c prime. So here we're going to kind of do a little bit of an algebraic trick that I'm going to show you. Since I said that this c prime is our integration constant, it just means that we need a constant. So we don't have to have e to the power of a constant. We can just rewrite this as a fully new constant, meaning that we can just take this term and simply say let e to the, or we can even do it one step further, let the plus or minus e to the c prime equal to c. That way we've handled this plus or minus at the beginning, and then we also kind of took this complicated looking term over here and just say let that be simply our integration constant. Because it's a constant, it doesn't matter what constant it is, so instead of having all this complicated kind of stuff over here, we're just going to say this is our constant c. Okay, so now as a result, we have that our p of y equals to, what do we have over here? We've got c times e to the x rx. And there we go. We've now solved for our generic form. So essentially here, since this is generic, our p of y or y, this just kind of represents our independent. This represents our dependent variable, and x is our independent variable. Okay. So now we have this. We have c as an arbitrary constant. So we're going to go ahead and move on and look at an actual example. So we're going to start by looking at this example over here, where we have y prime plus 3xy equals 2x. So we first need to determine whether this is a separable equation or not. Recall over here that our separable equations are in the form dy over dx equals to some function in terms of x and then multiplied by some function in terms of y. So we can right away convert this prime notation into Leibniz notation such that we have dy over dx plus 3xy equals 2x, meaning we have the derivative of y with respect to x. So now let's see if we can follow our step 1, which is to kind of separate our x and our y variables. So let's kind of do this in a couple steps. So we've got dy over dx. We're going to move this term over here to the other side by subtracting it. So we now have x minus 3xy. Okay, are we getting any closer to this form? Well, how can we turn this into a multiplication? We can see that we have x in both of these terms, which means that it can be factored out, which is awesome for us. So pretty much we will get x over here, and then what do we have left? We've got 1 minus 3y. And now this should be looking a bit similar. So we have our x over here is like our rx function, and then we got this piece over here, which is our py function, meaning that we have these two kind of functions, one in terms of x and one in terms of y. So that is great. That is like our first step. The next step we have to do is now to put all of our x on one side of the equation and all of our y on the other side of our equation. So let's go ahead and do that together. So right now we're at dy of dx equals to x times 1 minus 3y. Let's now take this piece over here and multiply it on both sides of the equation. That will give us dy equals to x 1 minus 3y, all multiplied by dx. Okay, we still have this pesky y term on our right side. That means we're going to have to divide this whole term on the other side of our equation. So we're going to divide this on both sides. This will give us now 1 over 1 minus 3y dy equals to x dx. So now we've successfully put all of our x terms on one side. So we have all our x terms on our right hand side, and we've got all of our y terms on the left hand side. So we are all separated and ready to go for step 2. So step 2 is we need to integrate both sides of our equation. Okay, so all we have to do there is now pretty much put that integral sign on both of our sides of our equation. So in the theory portion at the beginning, I showed the generic form, but in this example, we'll still kind of walk through the step-by-step process in how to integrate these terms. So we here have the integral of 1 over 1 minus 3y dy equals to the integral of x dx. So we're going to start off by looking at this integral because this one is a little bit more complex than our one on the right hand side. So in order to solve this one, we have to use a technique called U substitution. So what we're going to do here is we're going to say let 1 minus 3y equal to u. And now we need to figure out what is our du value, the derivative of u. So in this case, we take the derivative of this term over here. So du equals, so we're taking the derivative of u with respect to y, because y is our variable there. And that is simply, following the power rule, going to equal to -3. But again, we want to rearrange this such that we have dy by itself because we need to plug it in for this value of dy over here because we're using a u substitution. So in order to isolate for this dy, we get that dy equals to 1 over negative 3 du. Okay, all we did was multiply our dy up on this side and then divide our negative 3 over on our other side over there. Okay, so now we have our value for u, and we also have our value over here for our du and our dy. So what comes next? Well, u sub has its name. So pretty much wherever we see 1 minus 3y, over here we're going to sub in u. And then where we see our dy over here, we're going to sub in our value for dy, which we found over there. Okay, so we just have to do a little substitution. So now we have the integral of 1 over u, and then times we have to plug in our dy, which is negative 1 over 3 du. Okay, so now we're taking the integral of something that looks much simpler, and it will be easier for us to solve. So what we're going to do here is, following integration rules, is take this negative 1 over 3, since it's a constant, and bring it to the outside of our integral. So you have negative 1 over 3 times the integral of 1 over u du. And this is much easier to solve. So this over here is just simply going to equal, so we keep our negative 1 over 3 on the outside, integral of 1 over u is ln absolute value of u. Okay, so we've got this, and we'll just leave this here for a second while we go and tackle the integral on our other side. So we've now got this integral, and now let's focus on the integral of x. So let's look at that. So we now have the integral of x dx, and this just equals to 1 over 2 x squared multiplied, 1 over 2 x squared plus our integration constant c. So now let's put this all together. So we have our left-hand side and we've got our right-hand side, and now let's just write that all in one line. So that means we have negative 1 over 3 ln absolute value of u equals to 1 over 2 x squared plus c. And in this case, we're just going to call this c prime as we did in our theory section, because we know we're going to kind of change that value around for simplicity as we move on. Okay, so now that we've taken the integral of both sides of our equation, what's next? We want to isolate for y, because that is what we're trying to solve. When we solve differential equations, we want our answer in terms of our dependent variable. So, okay, so after we've done our u substitution, we can see that we have our integral still with respect to u, or the answer of our integral still with respect to u, but we want to solve for y. So all we have to do here is just do our back substitution. So we said initially, right, that we said that u equals to 1 minus 3y. So all we have to do is just plug that value back in. So that means we have negative 1 over 3 ln 1 minus 3y equals to 1 over 2x squared plus c prime. And again, this prime on the c does not indicate a derivative. It's just simply our initial notation for a constant, which we will be using throughout the rest of this example. So now we want to isolate for y. So the first thing we want to do is try to free up everything on the left-hand side. So that means we want to kind of get rid of this term. So to get rid of this, that means we have to multiply it, both sides of the equation, by positive 3. Or sorry, not positive 3, by negative 3, so that we cancel out the negatives. So that means we have ln of 1 minus 3y equals to negative 3 over 2 x squared, and then plus, or in this case technically minus 3c prime. Right away we're just going to take this because this is just a constant, and we're going to say let negative 3c prime equal to c, let's say double prime, for example. That way it's a constant, it doesn't matter what it is, but this is just a bit for simplicity's sake, plus c double prime. Okay, next thing we have to do is how do we free our y value from the brackets of ln. So what we do here is we have to bring everything into the exponent using e, because remember before I said that ln x, for example, e of ln x equals to x. So we want to bring that e so that the lns basically disappear. So what we end up with is the absolute value of 1 minus 3y, let's write our 1 like that, equals to e to the negative 3 over 2 x squared plus c double prime. And like I showed in our theory section, we can have this, we can get rid of the absolute value by taking the plus or minus of the value. So we now have plus or minus e to the negative 3 over 2 x squared plus c double prime. I also showed you previously how we can take this plus c and we can change this into two terms. So we have e to the negative 3 over 2 x squared multiplied by e to the c double prime. And like we did before, we're going to take this plus or minus in e to the c, and we're going to say let plus or minus e to the c double prime equal to c. Because a constant is just a constant. It doesn't matter what constant it is. And all this does is just make our equation look cleaner. Okay? So that means on our right-hand side, we now have c e to the negative 3 over 2 x squared. And on our left-hand side, we still have our 1 minus 3y. We're getting closer. We still need to isolate for y. So let's get rid of the 1. So we have negative 3y equals to c e to the negative 3 over 2 x squared minus 1, because we put it over to the other side. And now all we have to do is divide both sides of our equation by negative 3. So we are going to end up with y equals to negative c e to the power of negative 3 over 2 x squared minus 1 all over 3. And that is our final answer. We did it. So this is how you use separation, how you can solve a separable differential equation. In this particular case, we're looking at a first order differential equation. And yeah, so it helps you just kind of get a better feeling for kind of how all this works. And you can see that it's a great strategy. The first thing you have to do is just determine whether it is a separable equation. See if you can get it into that form dy over dx equals to a function of x times a function of y. And then you can follow the steps that I outlined in this video. So if you enjoyed this video, please drop a like and definitely comment any questions that you have, and subscribe for more of these videos. I'll see you next time.